I am recording this lecture to provide my students with additional source of information for getting prepared for the final exam. During the final exam, we will concentrate on control system design. And what's good about having a lecture recorded is that you can play it again and again until everything will be very clear to you. So the topic is control system design, and I will talk to you about pole placement. Why we call it pole placement? Because, as you remember, we will define dominant poles, we will define non-dominant poles, and this is the basis for our design procedure. First of all, I will take a very particular transfer function of the controlled plant. The stability issue of the control plant I'm not discussing with you. However, I want to make sure that there is no right-hand side zeros in the transfer function of the control plant, and there are none. The design specifications call for the settling time in the closed-loop system of 2 seconds and the overshoot of 10%. It also required that the error steady state tracking error should be under 0.01, whatever units are, for step reference, and the error for disturbance steady state also shall not exceed 0.01 for step disturbance. And the procedure we will start from the choice of desired dominant poles for the closed loop system. I will call these poles minus A plus minus JB. They should be complex conjugates. Why? Because otherwise we would never see the required overshoot. Now, from the settling time, I immediately can define the absolute value of the real part. You know that 4 divided by A, where A is the absolute value of real part, should be equal to settling time, and therefore A is equal to 2 in my situation. Now, for 10% overshoot, if you remember properties of the second order system, we should be able to define the damping ratio. There is a formula, but most students do not remember this formula. As a matter of fact, I don't remember this formula. The best what you can do is to look at the graph or look at the table, and during the final exam, if you will have a need to determine the relate overshoot to damping ratio, I'll give you a table. However, I know for sure that for 10% overshoot, the damping ratio should be equal to 0.6. And then there is a relationship between the imaginary part B and the absolute value of the real part of dominant poles. And this is the relationship. And this relationship involves the damping ratio. Where this relationship comes from? Take a second order system. The classical definition of the second order, canonical definition of the second order system. Take the poles. The poles will be 2 complex conjugates, and get the relationship between the imaginary part and absolute value of the real part. You will get exactly this result. Since overshoot should be 10%, and since for 10% overshoot damping ratio should be equal to 0.6, I will insert value of the damping ratio in this expression, and I will get something like 1.33. Now I know value of A already. It is 2. So value of B should be 2.66. And now I have the dominant poles established. minus 2 plus minus 2.66J. And then we have to realize that the control plant is a third order, and the system that we will design will be also a third order system, and a system like this supposed to have total of 3 poles. 2 poles are dominant, and the pole number 3 we can choose arbitrarily. It should be non-dominant, which means that its absolute value should be at least 4 times greater than the absolute value of real part of dominant poles. I chose minus 10, which is supposed to be fine. I want you to take a look at this symbol. This is a marker. Later in our design, we may decide that we need to change different non-dominant pole. And then obviously we would have to come back to this marker, or to this stage in our system design process. Now I have system poles, 2 complex conjugate dominant, 1 non-dominant, and I can build for you the desired characteristic polynomial of the closed loop system. I do this multiplication, and I'm getting this polynomial. You also must remember that the desired closed loop system transfer function could be obtained by making sure that the polynomial is right here, written right here, and in the numerator we're not supposed to have any zeros, and we only have to have the constant gain, and the constant gain should be equal to the zero order term of the polynomial denominator. Why? Because, as I told you in class, if I would replace s by 0 in the expression for the desired closed loop system transfer function, I'm supposed to get 1. All right, the next what you can see is the controlled plant, and according to our design procedure, the first thing that I have to do is to cancel zeros of the plant. So I will introduce this filter. Zeros are not located in the right hand side, therefore I have no problem with the pole zero cancellation. And this is the system that I will get. This is the plant with cancelled zeros. The next I introduce this polynomial feedback. The order of this polynomial in the feedback is supposed to be order of the plant minus 1. And this is the result. Can I get the closed loop transfer function for this system? Sure I can. And the closed loop transfer function is written right here. And you have to realize that I want this closed loop transfer function to be equal exactly to the desired closed loop system transfer function. How we do it? There are 2 ways of doing it. Well, 2 things have to be done to make it happen. First of all, I have to choose H2 coefficient, H1 coefficient, and H0 coefficient appropriately. And then I have to make sure that a constant gain is introduced equal to this zero order term. Look at this. I introduced the constant gain. All right. Constant gain is equal to the zero order term from the desired characteristic polynomial. And then I equate coefficients of the polynomial denominator of this closed loop system to the coefficients of the polynomial denominator of the desired system, and I'm getting values for H2, H1, and H0. So look, let's go back to our original system. This is the control plant. This is the filter that I use to cancel zeros of the plant. It's very explicitly spelled out, everything. This is the constant gain that I introduced. in the reference channel. This is the polynomial in the feedback. The only what I have to do now is to move the summing junction at this location. And this is what I do. And of course, when I do it, I have to follow the rules for block diagram transformation. And guess what I'm getting now? I'm getting the controlled plant. The output of the plant is Y. I'm getting the feedback, negative feedback controller. This is controller. And I'm getting filter in the reference channel. And I have a system that has exactly the same as the desired closed loop system transfer function. And if you don't believe me, you have to reduce this diagram, and I'm sure you will get exactly what our intention was. You will get this transfer function, this one. Now, take a look at the schematics, and the original closed loop system transfer function is done for the reference input, but there is also disturbance input. And unlike reference, disturbance is applied directly to the input of the controlled plant. The disturbance is applied where tires touch the road. The disturbance cannot be applied through the control circuitry. Control circuitry is very well protected from disturbance signals. So this is the place where reference is applied, their place where disturbance is applied, and this is the system out. And now we are ready to analyze steady state errors for step reference and step disturbance. First of all, when it comes to steady state errors, we have to come up with the transfer function for reference. And how you will do it? This is the input, this is the output. You have to figure out the transfer function. And this is the transfer function. And of course, don't be surprised. Our design procedure was properly performed, and therefore the transfer function for reference is exactly equal to the desired closed loop system transfer function. No questions about it. For the disturbance, I want you to take a look at the input. Input is here, output is here. So this is the forward path. This is the feedback. This module does not contribute into the disturbance business at all. If you will perform block diagram reduction properly, you will get this transfer function. This is the transfer function that relates the disturbance to the output of the controlled plant. And what I can tell you is this. In this situation, the disturbance transfer function has denominator of the desired closed loop system transfer function and the numerator of the controlled plant. In many cases, it works exactly this way, but don't trust it. I would prefer you to make your own derivation of both transfer functions. It's time to determine the steady state tracking error for the step reference. I'm saying it's always equal to 0. Let's make sure that it is. First of all, don't get confused about the formula for the tracking error. It's not a steady state error yet, it's just tracking error. It's equal to the reference minus system response to this reference. So reference in our case is step. Its Laplace transform is 1 over s. And here in square brackets I have 1 minus the transfer function for reference. And if I'm going through this operation, I have to do some algebra here. I will end up having this expression. I still have 1 over s. the Laplace transform of the step reference, and then I will have this expression. For the convenience, I pull out S from under the square brackets from this polynomial. Look, this term and this term will cancel each other. So this is the polynomial that's left. And from this polynomial, I pull out S just to make a point for the taking this limit. This is the steady state tracking error. I'm using the final value theorem. I have limit when S approaches to 0. This S belongs to the final value theorem. This is the Laplace transform of unit step reference, and this is the transfer function. And now we can figure out that this S will be canceling this S, and this S will stay uncancelled in the numerator. If S approaches 0, the steady state error will be equal to 0. So you see, if you designed a control system using the pole placement approach, and you did your design properly, the error, tracking error for step reference must be 0. Now I will consider with you the steady state error for step disturbance. And I am telling you, it's always equal to a non-zero constant. Let's make sure that it is true. The error for disturbance is equal to the system response to this disturbance. This is the disturbance. This is the transfer function for the disturbance. This is the Laplace transform of the step disturbance. And this is the disturbance transfer function. So if I would take limit of this expression, what will happen? This S and this S will cancel each other, and I will have in the numerator constant 3, and in the denominator I will have constant 110.756. And I can compute the error. And this is the moment when we should look at the design spec. And design spec calls for the error for step disturbance to be under 0.01, whatever units are. So our design failed in terms of the error for disturbance. What do we do in a situation like this? You know that the error could be manipulated by the choice of non-dominant poles. And I will show you just part of this manipulation. Initially, the non-dominant pole was chosen to be minus 10, excuse me. I will choose it now minus 20, and I'm going back to this symbol. Look, this is this point. This is this marker. Except last time the non-dominant pole was minus 10, now it's minus 20. And I have to go exactly through this procedure. Let's go through this procedure again. First of all, I have to establish the new characteristic polynomial of the closed loop system. It is quite different from what I used to have. The next, I will establish the desired closed loop system transfer function. And again, if in this expression I will replace S by 0, I'm supposed to get 1. And it is exactly the case. The next, what I have to do, I have to choose new values for the coefficients of the controller, feedback controller, H2, H1, and H0. And I'm doing it exactly the same way I did it before, except this time I have to equate 2 plus H2 to to 24, 2 plus h1 to 91, and so on. Let's see what happened. What will happen is this. Obviously, the characteristic polynomial of the closed loop system will be different, and it will be different for the transfer function for error, a transfer function for disturbance, and transfer function for reference. They both will be different, but I'm not that much interested in the transfer function for reference, because the tracking error, steady state tracking error, was equal to 0, and it still will be 0, regardless of the choice of non-dominant pole. However, the disturbance steady state error now will have a different value. If I would cancel this s and this s, in the numerator only 3 will be left. In the denominator I will have the zero order term left. 3 divided by 2 to 1 now is 0.135. We achieved significant reduction of the steady state error for step disturbance. We did not match the design specifications. We did not satisfy the design specifications yet. But what you have to do now? Now you have to go back to this marker again and choose different non-dominant pole, probably greater than minus 20 by absolute value. And you will have to go through the entire design procedure again, and eventually you would satisfy the design spec. The easiest way to follow this procedure is when you have a MATLAB script written already, and then you should be able to edit the script, run your MATLAB program again until you will get what you're supposed to get. Having MATLAB script is very important for your future work in high-tech industry, okay? You know, I did not match the design specs. I just showed you that the error for step disturbance is a non-zero constant, and you can manipulate this value of the error by choosing non-dominant poles. The next, I want to discuss with you what is happening if we're dealing with ramp reference and ramp disturbance. So first of all, I will change the definition of reference. This is in time domain. This is in the S Laplace domain. Beta is a non-zero constant. It's some kind of constant. Beta actually is the slope of the ramp. What do we do now? I'm looking at the tracking error. It's equal to reference minus system response to this reference. I'm going through this expression. I'm going through this expression. I'm going through this expression. And what I'm getting eventually for steady state error is this. I have this S of the final value theorem. I have beta divided by S squared, and I can factor out S from the numerator of the of this expression. So I have S and another S in the numerator. I have S squared in the denominator, and now in the numerator I have 51.756 constant. In the denominator I have 110.756. It still has to be multiplied by beta this ratio, and I'm getting this result for the steady state error for a ramp disturbance in the system. And you have to conclude with me that the error is a constant it's a non-zero constant. The problem with this error is the following. You have to take it or leave it. Take a look. It would be so nice if I would be able to change this value of the zero order term, and I could change it probably by choosing non-dominant pole. And it probably would change because of the choice of a different non-dominant pole. But take a look at this coefficient. This was the coefficient of the zero order term in the characteristic polynomial. But this one is the coefficient of the first order term. And if I would change the non-dominant pole, I am sure that this coefficient will change, but this one will also change. So we're getting into the situation when our ability to manipulate this steady state error is almost non-existent. By the change of non-dominant poles, we're changing both this coefficient and this coefficient, and how the new ratio between two coefficients will look like, it's very difficult to say. It's very difficult to say. And just for example, I will tell you what would happen if we would use minus 20 as the non-dominant pole. What will happen? This is the characteristic polynomial of the desired system. It was obtained earlier for non-dominant pole equal to minus 20. Look, the zero order term is twice as large as it used to be, or almost twice as large. But the term for s in the power of 1 also almost doubled. So the ratio is a little bit better, but not much better. So if I would be working on a realistic problem, I probably would keep trying, but this trial and error process could be very unsatisfying. Very unsatisfying. So don't overestimate our use of non-dominant poles in the situation when we have reference equal to a ramp. The next, let's concentrate on the steady state error. On the steady state error caused by a ramp disturbance. This is the ramp disturbance, or Laplace transform of the ramp disturbance. Alpha is the slope of the ramp. Error is defined as the system response to the disturbance. I have this result. I apply the final value theorem. And look what happens. I'm getting error equal to infinity, which implies that our system cannot handle ramp type disturbance. Something else has to be done about it. The next I want to discuss with you introduction of an integrator in the control loop. The integrator is a very powerful tool for manipulation of steady state errors. And the integrator physically is a power amplifier with the appropriately chosen, operational amplifier, not power amplifier, operational amplifier with appropriately chosen feedback. And you can always place it in the input of the control plant. Now, it is control circuitry. This integrator is part of the control circuitry. So disturbance surely cannot be applied through this integrator. Disturbance will be applied, as always, to the input of the controlled plant directly. But since we're getting into the control system design using the pole placement, we can do the following. Let's forget about the disturbance and concentrate on designing a system with the desired transfer function for the reference input. And since we will forget about the existence of disturbance, we can view this expression, this combination of two modules, as one modified controlled plant. It's not the real controlled plant. However, we will view this transfer function as the transfer function of the modified controlled plant. And now it is time to introduce dominant poles. And since design specifications overshoot and settling time did not change, I can use exactly the same dominant poles. But now order of the system is 4, and we have to come up with non-dominant poles. The definition of non-dominant poles, you know, we have to come up with 2 more non-dominant poles. And now I have to make a statement of warning. Multiple poles are not allowed. If you would introduce multiple poles, and later if you would look at the natural motion terms, among natural motion terms, you will have something like this. Something like this. You know what it is? It's a constant times time times exponential. It's not a pure exponential that we like to have. It's very difficult to discuss the convergence of this type of expressions, and in other words, having multiple poles would surely result in this type of terms in the natural motion, and surely will jeopardize the system dynamic behavior. So please don't use multiple identical poles when you do pole placement. So what I did in my study, I chose -10 and -15. And then I built the new characteristic polynomial. And then I built the new desired closed loop system transfer function for the reference input. And I still made sure that if I would replace s by 0 in this expression, I will get 1. This is important. The next, please take a look at this block diagram. This is the original controlled plant. This is the integrator that we did insert in the system. This is the filter that was introduced to cancel zeros of the controlled plant. The order of the system now is 4. And therefore, in the feedback, I would place a third order polynomial, h3 times s cubed plus h2 times s squared plus h1s plus h0. What do we do now? Now I understand that I have to find 4 values for coefficients h by making sure that this closed loop system transfer function will be equal to this transfer function. And I also have to introduce this constant gain exactly for the same purpose, for the same reason. I have to make sure that the closed loop system transfer function for this system, for reference input, will be equal to the desired closed loop system transfer function. The design is complete at this point. So, the introduction of the integrator increased order of the system by 1, And we introduced integrator expecting that this integrator will affect steady state errors. And now we will do the analysis of steady state errors for step reference and step disturbance for systems that have integrator in the loop. This is the transfer function for reference for our system, for this system that has integrator hidden inside. This is the transfer function for the disturbance. And I did everything correctly when I was obtaining this transfer function. Look, because of this integrator, I'm getting S in the numerator of the system, which will be important for our analyses. Transfer function for the reference, transfer function for the disturbance. The next what I will do, I would investigate steady state tracking error for step reference. And I can tell you it will be equal to 0 because this analysis is not much different from the analysis that we ran before. Yeah, look, the analysis is based on the exact expressions for the transfer function. I have to implement 1 minus g reference of S, and I'm eventually getting this S that sits in the numerator. Okay, and because of this S, when I will be using the final value theorem, I will get 0. And this is what I did here. I have this expression. I am assuming S approaches 0, and this is the S that will turn steady state error into 0. But you know what? I can give you even a simple explanation of this result. Take a look at this expression. I have reference 1 minus transfer function for reference. And if I would apply final value theorem, you know that G reference of 0 is 1, and 1 minus 1 will give you 0. So yes, error for step reference in the system with integrator or without integrator is 0. But now let's take a look at the error for step disturbance in the system with integrator in the control loop. This is the transfer function for the disturbance input. Don't forget, I told you this S sits in the numerator only because of the integrator that was introduced in this loop. 1 over S is the step disturbance. I can imagine this S and this S will be cancelled. Okay, but this is the steady state error. So I have exactly this expression. This S and this S are cancelled, but S that belongs to the final value theorem stays there, goes nowhere, it stays, and when it approaches 0, the entire error becomes equal to 0. And therefore you have to learn this lesson, that if you would introduce integrator in the control loop, and if you do the pole placement controller design, then you would surely make error for step disturbance equal to 0. The next that I want to do analysis of steady state errors for ramp reference and ramp disturbance for systems with integrators in the loop. Let's work on it. So first of all, we will assume that steady state tracking error for ramp reference beta over S squared, and I want you to, we're looking for the steady state tracking error, and I want you to keep in mind it will be a non-zero constant. Let's work on it. This is the tracking error. It's equal to reference minus system response to the reference. Reference is written beta over S squared in front of the square bracket. In the square bracket, I have 1 minus the transfer function for the reference. I'm going through this expression. I'm not making mistakes. Everything is done correctly here. Make sure that it is. And I will end up with this steady state tracking error. It is limit when S approaches 0. This S belongs to the final value theorem. This is beta over S squared. This is the reference. And this is what I used to have in the square bracket. 1 minus transfer function for reference. And we have this S in front of the expression. And now you can see that there is one S and another S in the numerator. There is S squared in the denominator. This S values will be cancelled. And what will be left is this. Beta will stay. Beta is the slope of the ramp. And then I have 876.89 divided by 1661.34, which gives me 0.528 times beta. This is the expression for the error for a ramp disturbance. Error is constant. Can we manipulate this error? Before you will say yes or no, let's figure out where these numbers came from. Please take a look at the desired characteristic polynomial that we obtained for the closed loop system. And this 1661.34 is the zero order term. But 876.89 is the term for S in the power of 1. And this is a bad news for us, because if I would try to manipulate this error, normally I would be able to change only this zero order term. Not in our situation. Not in our situation with the ramp. In our situation, what happens? If we change non-dominant poles, we will change this number, but we will also change this number. And we don't have much of a choice with respect to how these numbers will change. So yes, please acknowledge this fact. Our ability to manipulate steady state tracking error in the system with integrator or without integrator is limited. We don't have this freedom to manipulate the steady state error. It's a bad news for us. It's a bad news for us. But nevertheless, error will be constant, and this constant is not zero, is not equal to 0. Let's take a look at the situation. Let's take a look at the situation when we're dealing with the disturbance. And disturbance is a ramp function. And alpha is the slope of this disturbance. And I will show you that the error will be a non-zero constant. Not infinity, will be significant improvement comparing to the previous situation when there was no integrator. Now we do have integrator. Error will not be infinity. Error will be a non-zero constant. So what we do? Error for disturbance is equal to system response to this disturbance. It is disturbance, Laplace transform of disturbance times the appropriate transfer function. This alpha divided by s squared is the disturbance. This is the transfer function for this disturbance. We're going through algebra and we're doing the steady state error caused by disturbance. We have s of the final value theorem. We have s squared in the denominator. If you remember, this s in the numerator of the transfer function appeared because of the integrator, and as a result I'm getting a constant for you. This is a constant. The constant is equal to this coefficient of the numerator times alpha slope of the ramp divided by this zero order term. But amigos, this zero order term could be changed by changing the non-dominant pole or non-dominant poles. This coefficient that potentially could be affected by changing non-dominant poles is not involved in the definition of the error. So it's a good news. If you're not happy with this value, feel free to increase magnitudes of the non-dominant pole or absolute values of non-dominant poles, and you should be able to drive the steady state error for ramp disturbance to virtually any value you want. And you know what's good about pole placement procedure? If you would be doing this with a controller designed differently, we would be concerned about system instability. It's not the case. It's not the case. A system will stay stable regardless how much you will change the non-dominant poles. And now I want to talk to you about situations when system design specifications are expressed in terms of bandwidth and disturbance rejection. You know, specified system bandwidth is effectively a way to define the dominant poles of the desired closed loop system. This is how you should look at the system bandwidth. Because when you have a particular system bandwidth, you may choose one real dominant pole or two complex conjugate dominant poles based on the bandwidth. Nothing else to worry about. The rest of the poles must be non-dominant poles. So let's say that you have to have system bandwidth of 5 radians per second. What does it mean? It means that you have to have one real dominant pole equal to -5. Or let's say that you have to have bandwidth equal to 25 radians per second. That means only one thing, that you have to choose one real dominant pole equal to -25. Why? Because by choosing these dominant poles, we're forcing our system to behave exactly as first order system with the pole of -25 or pole -5 that has, with appropriate choice of constant gain, the bandwidth that was requested of us. However, it is possible to use bandwidth requirement to choose two complex conjugate dominant poles. I can imagine there are situations when you would prefer to have not one real, but two complex conjugate dominant poles. So you know what I will tell you? If required system bandwidth is omega radians per second, read the stuff, But the bottom line is this. You want your system to behave as a second-order system with natural frequency equal to this omega, or equal to the bandwidth, and with damping ratio equal to 0.8, 0.85. 0.8 is fine. Because in this case, the system will have the required bandwidth and no overshoot, because overshoot is not requested when bandwidth is specified. And with damping ratio of 0.8, the overshoot is cannot be seen at all. So basically, if you have bandwidth requested to be equal to omega, this means that dominant poles should be poles of this second-order polynomial, where damping ratio is equal to 0.8. And if you will go further with this very unsophisticated derivations, you will see that with bandwidth equal to omega, you have to have two complex conjugate dominant poles. The real part is equal to minus 0.8 times omega plus minus 0.6 times omega times j, two complex conjugate poles. For example, if the required bandwidth is 10 radians per second, the choice of two complex conjugate dominant poles is straightforward. Minus 8 plus minus 6j. And so on. The rest poles, of course, are non-dominant poles. And the number of non-dominant poles depends on the order of the control plant. And then you need a constant gain and no zeros, of course, in the desired closed-loop system transfer function. No zeros. But the constant gain should be chosen such that if in the desired closed-loop system transfer function you will replace s by 0, you will get 1. G closed loop of 0 must be equal to 1. When it comes to disturbance business, we use disturbance rejection. And disturbance rejection is not something that you can address analytically. Disturbance rejection you can assess by running the body plot, running the system frequency response for the disturbance input. So it's not analytical, it's basically a purely computer-based procedure. And now I want to do an example with you. I have exactly the same control plan that we looked at in the past, but this time design specifications are system bandwidth is 15 radians per second and disturbance rejection is 20 decibels. Let's see how a system design would look like. I can look at the 15 radians per second and immediately define two complex conjugate dominant poles, minus 12 plus minus 9j. And you know why. Now, I can easily define the non-dominant pole. We need total of 3 poles. The non-dominant I will use minus 50. 50 is 4 times greater than 12. No problem. At this point, I am ready to define the desired characteristic polynomial of the closed-loop system. It's written right here. And now I can define the desired closed-loop system transfer function. And by placing this value 11 to 50 in the numerator, I'm making sure that the G closed loop for s equals 0 is equal to 1. The next we're going through cancellation of plants zeros like we did it before. This is the control plant with cancelled zeros. This is the constant gain that we insert in the reference input. This is the second order polynomial that we place in the feedback of the system. We know that the closed loop system transfer function should be equal to the earlier obtained expression, specifically to this expression. To achieve this goal, we have to make this k, constant gain, equal to 11250, and coefficients h2, h1, and h0 should be defined as shown here. And this is the complete design, except what's missing here? Couple of things is missing. I did not show here the filter that we use to cancel zeros of the control plant. We show here plant with canceled zeros already, which is no good. Now, this polynomial mathematically could be placed in the feedback of the system, but there is no physical system that has only zeros and no poles. So we have to fix both shortcomings. Here I recalled and took into account the filter that was used to cancel zeros. Then I moved summing junction to the input of the controlled plant. And guess what? Now you can see the control system block diagram with the exact transfer function of the controlled plant, with the feedback controller, and with the filter in the reference channel. This is our final result, final product. Now, can we come up with the transfer function for the reference and transfer function for the disturbance for this system? Sure we can. Transfer function for the reference is, as you know, equal to the desired closed loop system transfer function. I wrote it right away. If I wouldn't, I probably can get the work on this transfer function and get the same result. Now, this is the transfer function for the disturbance for the closed loop system. This is the transfer function that relates to this point where disturbance is applied to the output of the system. Now, in order to, my design is, I'm done with the design. However, I want to demonstrate for you that the obtained system has exactly the required bandwidth and happens to have the disturbance rejection that is acceptable. How to do it? I have to take this transfer function and convert it into a body plot. And then I will take the transfer function for the disturbance and will convert it into a body plot. And I did both. First of all, I want you to see the frequency response of our system for the reference input. It has exactly 0 decibels until the frequency, which happens to be 14.75, which is virtually 15 decibels. Virtually 15 radians per second, the bandwidth of the system. And then we have minus 40 decibels per decade. So effectively, our system in terms of dynamics for the reference input behaves as a second order system with natural frequency equal to 15 and damping ratio equal to 0.8. It's a perfect validation of our design. When it comes to the disturbance rejection, I got the frequency response for our design system for the disturbance input. And this is what I have. What you can conclude by looking at this frequency response is this. The entire magnitude of the frequency response of our system is below minus 30 decibels. So we can claim that we have 30 decibels, not minus 30 decibels, 30 decibels disturbance rejection, which means that every single harmonic of the disturbance will be reduced by our system, at least by 30 decibels, and most of them will be reduced actually even to a great extent. So at this point, I am done with our design, and you are done with my lecture on the pole placement applications for controller design. So I hope you will review it at home. You can watch this video more than once, of course, and I guess you will be prepared for the final.